Here's some quick review on the atomic structures we have learned. You have the nucleus, and the nucleus is the center of the atom, and it is so compact, so dense, and what is in the middle is you have your protons and your neutrons, and your protons are positive charge, your protons are your atomic number, and your neutrons are neutral. To calculate the number of neutrons, you need to know the atomic mass minus the atomic number. And finally, we have the electrons. The electrons are located outside the nucleus, and they go around in orbits or electron clouds, and electrons are negative charge, really have no mass at all, and in a neutral atom, they are the same as the number of protons. I saw this joke online, and I don't know if it's just me, but my chemistry humor, I found this so funny. So one says, "Oh my gosh, I've lost a neutron." The other atom says, "Don't worry, you can get a new one, free of charge." That's hilarious. That's hilarious. Now's the time for shout outs. Maggie, wake up. Fula, wake up. And don't forget Lauren. I need everybody up, up, up. And Jack, that fish is for you. Radioactive decay is really kind of interesting because they refer to the atom that is going to lose energy or radioactivity as the parent atom. I don't know why they feel like the parent is the explosive one. That just doesn't make sense to me. But that's what happens in radioactivity. This is a basic drawing of radioactivity. You have your parent atom and that little nucleus there. If that strong force that is holding that nucleus together, and let me write that down, the strong force. The strong force is the force that holds the nucleus together. And if that strong force somehow breaks, sometimes it's by a high-speed neutron, sometimes it's just by the instability itself of the nucleus, and when it breaks, it forms a new atom, and we call that new atom the daughter product. And with that strong force release, we now get some electromagnetic energy, some radioactivity, some energetic particles going to be released, and we're going to talk about those particles. Here's an example of kind of what a radioactive nucleus kind of looks like. In picture number 1 down here, we have the protons and the neutrons kind of swarming around. They come together and they form a nucleus. When they form this nucleus, they get a strong force. Think of it as like a little protective force, or like almost like it's under like a saran wrap, and it's all kind of held together. Very, very strong. Well, if it becomes unstable due to an outside force smashing into it, or just the compact and the density of this, it just cannot hold it any longer. The nucleus starts to release this energy, all this yellow energy. The nucleus tries to release it. And when it releases it, it's trying to force itself to become more stable. It's like a nucleus saying, "Oh, I'm going to explode." And it explodes, it releases a little bit of energy and says, "Oh, I think I can hold this." And so you have a nucleus that's kind of really big and really, really, really compact. It releases some energy, and after it releases that energy, it is able to now form a smaller, more stable nucleus. But you got to remember that released is going to be some type of energy. This energy is not always good, and we're going to talk about 3 different kinds of particles. I know when we start thinking of radiation, the very first thing we think of is, well, The Simpsons. You know what? They go and portray that radiation is green and just glows. It doesn't. It's actually something that we cannot see. It is so small, and the Simpsons have given it kind of the wrong picture that we're thinking about. Still a great show, though. There are different type of particles that we're going to look at. We're going to look at alpha particles, we're going to look at beta particles, and we're going to look at gamma rays. First off, we talked in class a little bit about being reactive and some things that just kind of make you lose it, make that strong force that we have kind of explode. Maybe someone like Christina. If Christina's about ready to lose it because she has way too much on her plate, she's going to explode, and she might explode on some of her friends. And that would be actually really gross. Some of you were all mad because in one of our classes we had our Francisco team just crushed and dominated you in writing the protons, neutrons, and electrons. So maybe you're going to be a particle or radiation source and explode. Here we have our atom. When we have our atom, it has that strong force like we said before, and it can release some particles. One of the particles is an alpha particle. Alpha particles are represented by 4, 2, H, E. Why an alpha particle is released is because the atom is so big that it wants to release something big. And a big thing that it can release of energy, the biggest type of particle it can release, is a helium particle. Atomic mass of 4, and it has 2 protons. The atomic number is 2. The next is a beta particle. Beta can be represented by a 0 mass, -1 charge, and it's an electron. I'm going to explain beta particles in 1 second, and the last one has no mass, no charge, and it is called a gamma ray. If I was to get you with an alpha and shoot an alpha at you, it's a helium atom. A piece of paper could stop a helium atom. Your skin could stop a helium atom. It is not going to be harmful to you. But if I had a beta gun and I shot you with some beta particles, the layer of clothing or a few millimeters, such as aluminum, that could basically stop it. You can see that it is getting into the hand up to about this point. So beta particles can do more harm to us. Gamma rays, though, can go right through. It goes right through our tissues and our bones, and it can even go through some concrete. And so we're going to talk about that also, the gamma rays. So our first particle is alpha that we're going to talk about. Let's say we have an element called uranium. Its atomic number is 92. Let's say its mass is 298. This is a huge, huge element. It has 92 protons in it, and then it has even more neutrons shoved into that nucleus, and it can't hold it anymore. And what happens is we have an alpha particle is released, kind of to give it some pressure. Alpha can also be represented by a little fish. Then we got to figure out what is going to be the product that's left over. Here you have an atom. Let me show you the atom. So you have uranium atom. Uranium releases some energy, and that's our alpha, but in the same process, it forms a smaller nucleus. Due to the law of conservation of matter, the atomic number and the atomic mass cannot be lost. If we look at the top example, we see that on the bottom, uranium has an atomic number of 92. Helium has an atomic number of 2. In order for no matter to be lost, we need to look at an atom that has atomic number of 90. 90 plus 2 equals 92. Element 90 is thorium. You look at the periodic table and you look up element 90. On the top now, we got to say what isotope of thorium is formed. Uranium's original mass is 298. Well, 4 atomic mass units go to helium. How many are still needed? 294. 294 plus 4 is 298. Let's do another example. If I have thorium, 90, let's say it has a mass of 290. And I'm going to tell you that it releases and decays a helium atom. I want to know what is, we call it the daughter particle. You have the main parent particle of thorium, and it releases into a daughter particle. Well, on the bottom we have 2, and on the bottom on the other side we have 90. I know that 88 plus 2 equals 90. Then I look at the top, and I know that I have 290 to start. 4 plus what is 290? 286. And we look on the periodic table, we find element 88. Next we have a beta particle. Beta in an equation is represented as 0 over minus 1 e. It is an electron. Let's picture a nucleus. In the nucleus we have protons and we have neutrons. In an unstable nucleus, sometimes the neutron will be converted into a proton. So no longer is the neutron going to be neutral. Now it is a proton, and it becomes a proton. Well, a neutron is made up of equal number of protons and electrons. And so therefore, it spews out an electron. So, going back and to look at a beta particle. This time we're going to start off with radium. And radium is element 88, and we're going to give it a mass of 226. And let's say it has an unstable nucleus, and it is going to decay a beta particle. Again, we just have to make sure, due to the law of conservation of matter, that no matter is lost. So we have a minus 1. If I take 89 plus a negative 1, it gives me 88. And 226, a beta particle, an electron, has no mass. So the mass is the same. 226 plus 0 is 226. In order to figure out which element I've written, I have to find element 89 on the periodic table, and that is element AC. Last but not least, we have a gamma particle. So gamma is represented, kind of looks like this, or sometimes I'll do that in class. And gamma has 0 mass and 0 charge. So again, if I start with element 88, radium, 226, and I said, oh, it was unstable, and it released a gamma ray, we would just do gamma. You could do 0, 0, but most of the time we don't even include that at all. Sometimes we can have an element that could lose all of them. Let's do something, for instance, like element Pu. Let me get rid of this. Okay, let's do element Pu. Pu is number 94. We're going to say 244 for the mass. And we're going to write that it loses and it decays an alpha, a beta, and a gamma. And my question to you is, what's left? This looks hard, but it's really not. On the top numbers, I have 4 plus 0, which is 4. On the other side, I have 244. I know that 240 plus 0 plus 4 equals 244. On the bottom, I have 2 plus a negative 1, and that gives me a positive 1. On the other side, I have 94. I know that 1 plus 93 is 94, so it's element 93. I go and find element 93 on the periodic table, and I see that it is NP. Oh, I ran out of room. Let me write that again. 240 over 93, NP. We're going to do a lot more of this in class. Be ready to do some writing, and we'll do more shout outs on the next video.